In an experiment to measure the specific heat capacity, in an experiment to measure the specific heat capacity of water, a student used an electrical heater to heat some water. I take it again. In an experiment to measure the specific heat capacity of water, a student used an electrical heater to heat some water. His results are shown below. Calculate a value for the heat capacity of water. So calculate a value for the heat capacity of water. Comment on any likely sources of error. 1. Calculate a value for the heat capacity of water and comment on any likely sources of error. Mass of beaker is equal to 150 grams. Mass of heater 150 grams. Then mass of hello, let me take it again. Did I say mass of heater?
Yes, please.
It's beaker, mass of beaker. Mass of beaker 150 grams. Mass of beaker plus water. Mass of beaker plus water 672 grams. 672 grams. Then current.
What is 672 grams?
Yes, mass of beaker plus water. Beaker plus water. 672 grams. And then current in the heater. The current in the heater is 3.9 ampere. So I is 3.9 ampere. Potential difference across the heater. That's the voltage. The voltage across the heater is 11.4 volts. Initial temperature. Initial temperature T1 is 18.5. The final temperature T2. The final temperature is equal to 30.2 degrees Celsius. And the time is equal to 13 minutes. 13 minutes. So the question asks you to calculate a value for the specific heat capacity of water and comment on any likely sources of error. Comment on any likely sources of error. Pamia.
Please, was the mass of the water alone given?
No. Mass of the mass of
both the beaker and the water was given.
Yes, mass of beaker is 150.
Yes.
Mass of beaker alone 150 grams. The mass of beaker plus water 672.
Yes, please. Thank you.
Welcome. So make me proud.
Mr. Dear.
Mr. Ayi. Mr. Leslie.
Please, can you drop the question on the platform? I didn't get it.
Mpebrel. I hear. Leslie, you did not show up yesterday. What's your secret?
Yes, please. Please, I was not feeling well.
Who told you? Who told you that you were not feeling well?
The Lord said this is not for it's not for
Isaac Atta. Hmm. Oh, I'm coming. Leslie, the phone is giving me trouble. Just for taking a shot of it, it will not allow me. Oh, no, 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 no. Leslie, you are not fortunate. You are still to write. So I'm reading.
Yes, please.
In an experiment to measure the specific heat capacity of water, a student used an electrical heater. A student used an electrical heater to heat some water. His results are shown below. His results are shown below. Calculate a value for the heat capacity of water. 1. Calculate a value for the heat capacity of water, and then comment on any likely sources of error. 1. Mass of beaker is equal to 150 grams. Mass of beaker plus water is 672 grams. Current in the heater equals 3.9 ampere. Current in the heater equals 3.9 ampere. Potential difference across the heater, that's the voltage V, is 11.4 volts. Then initial temperature 18.5 degrees Celsius. Final temperature equals 30.2 degrees Celsius. The time taken equals 13 minutes. So use this information to determine the specific heat capacity of water and then comment on any possible error. That is the problem of the day. Just make me proud. Just in doing so, the student heated some volume of water. Okay, and these are the data. Now, use this to calculate or determine the specific heat capacity of water, and then comment on any possible error. So clearly, the student tried to use electrical method in determining the specific heat capacity of water. Okay, we use the electrical method in determining the specific heat capacity. Here, a certain volume of water is heated using an electric heater in a vessel. So the electrical energy must be equal to the heat gained by water. And what is the electrical energy? The electrical energy provides the heat energy. And so here we have the electrical energy being equal to, the basic relation is that E is equal to power times time. So we will use this formula if we had been given power. The power is also equal to current times potential difference, voltage. We have the current, we have voltage. And so we can calculate for P, meaning that the electrical energy, which is I times V times T, must be equal to the heat gained by water, which is MC delta T. So understanding this, you are good to go. I is 3.9. The voltage is 11.4. Time is 30 minutes, but we'll have to change it to SI units, seconds, so as to match all other quantities. Okay, so change 30 minutes to seconds for me. Isaac Atta, what is 30 minutes in seconds? Isaac Atta. Anybody? 30 minutes in seconds.
780 seconds.
So this is 780. Now, the mass of empty beaker is 150. Mass of beaker plus water is 672. How do we determine the mass of the water? Calvin, how do we determine the mass of water? We are given the mass of the empty beaker as 150 grams, and the mass of beaker plus water is 672. Calvin, how do we determine the mass of the water? Or Calvin is not here. Yes, anybody else? Anybody? Oh, the mass of the water. How do we determine it? Frida, Eva, Princess, Prince, also answer, Millicent. How do we determine the mass of the, yes, Mamia?
If the mass of the beaker and water
minus
subtract the mass of the beaker subtracted out of the mass of the beaker and the water.
so what will be the value?
0.522 kilograms.
So yes, thank you, Mamiya. It's actually 522 grams, but since we are changing all other quantities to SI unit, we must also change the mass from gram to kilogram. So 0.522, we are looking for C. Now, for change in temperature, whether it's in Kelvin or degrees Celsius, the value is the same. So change in temperature will be equal to the final temperature, which is 30.2 minus 18.5. So here, there's no need of us converting from degrees Celsius to Kelvin because change in temperature is 1:1. Okay. So what is 30.2 minus 18? 18.5.
11.7.
Pardon?
11.7.
So this is equal to 11.7 either degrees Celsius or Kelvin. So C therefore, this is times 11.7. C would be equal to, give me this product, 3.9 times 11.4 times 780. Let's be quick. Oh, Leslie and Co. Don't waste time. Oh.
34,678.8.
So 3, 4, 6, 7, 3, 4, 6, 7, 9. I'm running it. Divided by this times this. 0.522 times 11.7.
6.107.
Or 6.1074. 6.1074. So when you divide the numerator by the denominator, and then tell me whatever will be there as the specific heat capacity of water.
Five thousand six hundred and 5,678.2.
5,678.2 joule per kilogram per Kelvin. Okay. What we are to comment on the sources of error, possible sources of error. What are some of them? Under this experiment, what do you think are some of the possible sources of error? Yes. Anybody? What are some of the possible sources of error? Mamiya.
Parallax error when you are reading the beaker.
Oh, Mamiya, here we will not read the beaker. 'Cause. 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 ' You see, here we have to weigh to determine mass of beaker and mass of beaker plus water. And in doing so, we have to use the electronic balance. And the electronic balance, you know, is digital. So Power's error wouldn't occur here. Okay. More views. What do you think will be a possible source of error? Okay, let me give you one. One possible error would be that, you see, this principle of calorimetry works on isolated system. If the system is not well insulated and heat energy can move from the surrounding to the system or move from the system to the surrounding, it will affect your results. So because the system and the study is not well insulated, it's not well isolated, that alone can introduce a certain source of error. I want one of you to brainstorm, think, and then tell me another clear, obvious, okay, distinct error. There is another clear and there's such a distinct error which would also occur in this case. Can somebody help? Michelle, Eva, you are all here. Isaac Atta, I called you. You never contributed. Chairman, Crispin, Calvin, Bridget, Princess, Prince. Okay, you see, another possible error is that we have because you see, the specific heat capacity of water must be around this. But it is 5,000 and some coins. You see, because we also ignored the heat gained by the beaker, it will also introduce an error. We are only looking at the heater heating the water. Meanwhile, the water is within a beaker, and the beaker would also be heated up. So because we did not take the heat energy gained by the beaker, it will also serve as a source of error, okay, in whatever we are doing. Please, are you okay? Class, are you fine? Hey, am I talking to people? So,
Yes,
so
please.
the two possible errors will be poor insulation, because the system is not done in an isolated system. Okay. So poor insulation. Two, because we also ignored the heat gained by the beaker itself, it would also introduce an error into whatever we are doing. Okay. Usually, let me draw your attention to this so that when you meet such a question, you can also relate. When a bullet is fired by a gun, class, what provides the kinetic energy by the bullet? When a bullet is fired, oh, what provides the kinetic energy the bullet moves with? Yes. Anybody? a bullet is fired, and then the bullet moves with that gargantuan speed. What provides the kinetic energy of the moving bullet? Isaac Carter, you are not talking. It's a pity. Speak. Just please, let's express our views. You may be right, you may be wrong. It's part of the game. Don't be silent. Let's share ideas. I'm not a friend of this kind of teaching where I'll only do the talking. No, you know. Yes. Anybody apart from Mamiya? Mamiya has been contributing a lot. I think I must award Mamiya. When a bullet is fired, what provides the kinetic energy of the bullet? Okay, Mamiya, since Leslie, you are also here. Leslie, go ahead. Let's hear from you.
Yeah.
Yes.
Please, I think it's the chemical energy that is stored in the bullet.
The chemical energy is what does the gunpowder. I heard Crispin, I've seen what you sent. Okay. When a bullet is fired, when it hits a target, it gives out fire. It goes with fire. The fire aspect of it is the burning of the gunpowder, which is the chemical energy. But the speed with which the bullet itself moves with is not by the chemical energy. Okay. If you have gone into bullets gun before, a gun has a spring. So when I've forgotten the name given to that knob, which is pulled back and released. If somebody knows, send it to me. So when you press that knob, what you are doing is that you are compressing the spring. When you release it, okay, the spring force trigger. Thank you, Prince. You are a military guy. So when the trigger is released, okay, the spring enlarges. So it compresses and then extends. So it is the elastic force, okay, is the spring force which hits the bullet and then sets it into motion. So you pull the trigger back and it compresses the spring. So it's similar to the trap door. When you compress it and release it, it moves with some force. That's the spring force. So it's the spring force which is converted to the kinetic energy of the bullet. Now, when a bullet is fired and it hits a target, sometimes because of the burning chemical reaction, the gunpowder, it can burn a certain target. The target. Okay. So here we are looking at the kinetic energy of the bullet converted to heat energy, which is given to the targets. Okay, so sometimes we can also have acquisition of heat energy due to the conversion of kinetic energy to heat energy. It can also be potential energy obtained by a particular body upon its impact with another. Potential energy is converted to kinetic energy, which heats up a certain. I have a question to this effect. I want to give the question to you to draw your attention to some of these things, so that when you see it, it will not be alien to you. I have this interesting question under this. Give me a minute to retrieve the question, please. Okay. Please, I'm reading. A cowboy fires a silver bullet. A cowboy fires a silver bullet with a mass of 2.00 gram and with a muzzle speed of 200 muzzle speed. A cowboy fires a bullet of mass 2.00 gram with a muzzle speed. The muzzle speed is just the speed of the bullet. Muzzle speed of 200 meters per second. Muzzle speed of 200 meters per second into a wall of a saloon. He fires the bullets of this mass of this speed into the wall of a saloon. Assume that all the internal energy generated by the impact. Assume that all the internal energy generated by the impact remains with the bullet. What is the temperature change of the bullet? What is the temperature change of the bullet? Okay. So a cowboy fires a silver bullet with a mass of 2.00 gram and with a speed of 200 meters per second into the wall of a saloon. Assume that all the internal energy generated by the impact remains with the bullet. What is the temperature change of the bullet? Now take the specific heat capacity of bullets, of silver. The specific heat capacity of silver, where is it? Where is it? I'm coming, let me get the specific heat capacity of silver for you. The specific heat capacity of silver is 2,400 joules per kilogram per Kelvin. 2,400 I'm coming now. Oh, sorry. It is 240. Please, pardon me. It is 240. 240 joules per kilogram per Kelvin. The specific heat capacity of silver, solid silver, is 240 joules per kilogram per Kelvin. Then the B question, question 2, is a follow-up of the same question. Suppose that the cowboy runs out of silver bullets and fires lead bullets of the same mass. Suppose that the cowboy runs out of silver bullets and fires a lead bullet of the same mass and at the same speed into the wall. What is the temperature change of the bullet? So suppose that the cowboy runs out of silver bullets and fires a lead bullet of the same mass and at the same speed into the wall. What is the temperature change of the bullet? Take the specific heat capacity of lead to be 130 joule per kilogram per Kelvin. Take the specific heat capacity of lead to be 130 joule per kilogram per Kelvin. Make me proud. So simply, this is about energy conversion. So a cowboy fires a silver bullet of mass. So mass of silver. Mass of silver. This is 2.0 gram. And with a muzzle speed of, so speed of bullets is 200 meters per second. Into the wall of a saloon. Assume that all the internal energy generated by the impact remains within the bullet. What is the temperature change of the bullet? Okay, all that is being said is that we are looking at when the bullet is fired and then upon impact with the wall, okay, upon impact, all the kinetic energy will be converted to heat energy. And it is the heat energy which will raise the temperature of the bullet. Okay, So we have kinetic energy of the moving bullets converted to heat energy, which will raise the temperature of the bullets. So we are to determine the temperature change. So over here we have the kinetic energy of bullets would be equal to the heat energy gained after impact. After impact. Heat energy gained by the bullet after impact. So what is kinetic energy? Half mv squared must be equal to the heat energy gained by the bullet mc delta t. Now, interestingly, this mass of bullets would cancel out, so that we are looking for delta t. Delta t therefore would be equal to v squared over 2c. When we make delta t the subject, we must divide through by c. So the speed is 200 meters per second divided by 2 times the specific heat capacity of lead. And what did I give you as the specific heat capacity of silver? What's the specific heat capacity of silver?
240 joule per kilogram.
So 240. So please quickly do the calculation for me. Do the calculation for me. And the change in temperature must be 83.3 degrees Celsius or Kelvin. Okay. 83.3 degrees Celsius. That's the answer. So such questions usually not difficult. Now the next follow-up question is that suppose the cowboy runs out of silver bullets and fires lead bullets of the same mass and at the same speed into the wall. What is the temperature change? So all that will change under this situation is the specific heat capacity. So if he fires lead bullets, we have the change in temperature being equal to 200 squared divided by 2 times. What's the specific heat capacity of lead?
130.
130. And what is the answer here? What's the answer if he fires?
The formators force.
153.8. 153.8.
150.
3.
Okay. 153. So up
Point
0.8. So
Standard, we make that.
0.8. Yes, please. 0.8.
so approximately 154 degrees Celsius. Okay. So such questions not difficult at all, but it is your understanding of energy conversion and so on and so forth. Please, any question? No question. Do I clean the board? Because we are going to continue with our change of state. Do I clean it? Okay. So change of state. Change of state. So yesterday we went through different processes where one state can change to another. And we talked about fusion or melting. We discussed. Now, every change of state occurs at a constant temperature. Change of state. Every change of state occurs at a constant temperature. What do I mean by this? When you put water on fire and then you insert a thermometer, this is the thermometer. As the water gets heated, you realize that the thermometer reading would also be rising. The thermometer reading would also be rising. Now, the moment the temperature gets to 100 degrees Celsius, the thermometer reading will not change. It will be constant. It will be constant. Now, at 100 degrees Celsius, which is the boiling point of water, at this particular temperature, the state of water from liquid is changing to gaseous. And once change of state begins, the temperature must be constant. Okay? The temperature must be constant until every liquid water has turned to vapor. Okay? So every change of state occurs at a constant temperature. And change of state begins at a particular temperature. This temperature, okay, can be either the boiling point, freezing point, melting point. So we describe boiling point of a substance as the temperature where change of state begins. Now, last time I explained to you what we mean by sensible heat and latent heat. With sensible heat, we are looking at the amount of heat energy which changes the temperature of a substance. Any amount of heat energy which changes the temperature of a substance. Okay, so here the change can be an increase in temperature or a drop in temperature. So long as the temperature changes, that source of heat energy is what which is causing the change is described to be sensible heat. Now, latent heat. Latent heat is that source of heat energy which changes the state. And before we go into latent heat, the source of heat energy which changes the temperature of a substance actually causes a change in the kinetic energy. So when you put water on fire and you heat it, as a heat supply increases, it's so much absorbed by the liquid, you realize that the water will be, there will be bubbles from up coming from beneath the saucepan and then coming up. Okay. As the liquid absorbs heat energy, it's the kinetic energy of the water molecules would also be increasing. So sensible heat, okay, affects the kinetic energy of the molecules. Now, because kinetic energy of molecules is directly proportional to absolute temperature, it means that as the kinetic energy of the molecules increases, the temperature also increases. When the kinetic energy of molecules is dropping, the temperature will also be dropping. Now, latent heat. The substance absorbs heat energy and then its temperature changes and gets to maybe the boiling point. Let's take water as an example. When it reaches this temperature, which is known as the boiling point, the temperature will not change again. It will be constant. Even though the liquid on fire continues to absorb the external heat energy. Okay? Meaning the absorption of heat energy will not cease. But at this temperature, no amount of heat energy would change the temperature. The temperature will be constant. What it means is that the extra heat energy being absorbed does not affect the kinetic energy of the molecules. Rather, it goes to work on the potential energy of the molecules rather. Okay, how does it affect the potential energy? If the substance absorbs heat, the extra heat energy absorbed at this temperature breaks the bonds between the molecules. So if it is liquid and the bonds are broken, the molecules now are free to move about. As they are free to move about, it's a transition from the state of liquid to gaseous. And this amount of heat energy, which is responsible for changing the state or phase of a substance, is what we describe as latent heat or sensible heat. So, whereas sensible heat increases kinetic energy or changes, instead of increases, let me use changes. Ke of molecules, latent heat also changes the potential energy of molecules of a substance. So if the PE of molecules is changing, then it's an indication that there is a phase change. If the Ke of molecules changes, there is an indication of change in temperature as well. Please, is there any question? All right. Substances. So, you see, last time I told you that burns or injuries sustained from boiled water to any degree is less severe compared to burns sustained from vapor. This is because water vapor has both sensible heat and latent heat. Okay, it has both. Whereas boiled water only has what we call as sensible heat. So it means that vapor has enough heat energy compared to boiled water at temperature less than 100. Okay, so this is the reason why burn sustained from vapor is more severe than burn sustained from boiled water. All right, now let's look at latent heat of
Please, is it possible to heat gas? And if you heat the gas, what will happen to the gas?
If you have a chamber, gas chamber, you can heat it. When you heat it, okay, the temperature would actually change, increase. If it is absorbing, okay, well, you are heating. So its temperature would increase. Okay, but change of state for gas, because it's gas isn't visible. If it is changing another form, you can hardly see it. But you can keep gas in a chamber and heat it. All right.
Yes, please.
All right. Let's look at latent heat of fusion and latent heat of vaporization. Fusion is about melting. So fusion is melting. Melting. And melting is a process whereby solids change states to liquid after absorption of heat energy. Now, substances can absorb heat energy differently to change states. Okay, so when we talk about latent heat of fusion, we this
You are live to people.
Oh, please mute yourself. Latent heat of fusion refers to the quantity of heat energy, okay, that must be absorbed by a substance at its melting point, okay, in order to change state from solid to liquid at a constant temperature. So, latent heat of fusion refers to the quantity, the amount of heat energy that must be absorbed by a substance at its melting point. And this is important because change of state occurs at a particular temperature, and that is either the melting point. So at its melting point, in order to change state from solid to liquid at a constant temperature. This is also similar to heat capacity. If we talk of heat capacity, we are looking at the amount of heat energy that must be absorbed by a substance to raise its temperature, okay, by 1 degree Celsius or 1 Kelvin, okay, to raise its temperature by 1 degree Celsius or 1 Kelvin. And this is for any given mass, okay? So under change of state, when we talk about latent heat or fusion, we are also looking at the amount of heat energy that must be absorbed by a substance at its melting point in order to change state from solid to liquid at a constant temperature. Now we also have what is known as specific latent heat of fusion. I want somebody to help me. Specific latent heat of fusion, represented by the symbol L subscript F. What do you think is the definition of specific latent heat of fusion? If latent heat of fusion generally is this, what would be the definition of specific latent heat of fusion? Anybody to help? Oh, specific latent heat of fusion. Hey, everybody is quiet. Calvin, are you there? Hello, Calvin. Okay, Leslie, I want you to try. What do you think is specific latent heat of fusion?
Mr. Dia, please, I think I'll define it as the quantity of heat energy that must be absorbed by a substance at its melting point in order to change state from solid to liquid without its temperature changing.
Okay, nice try. Anybody else? What is specific latent heat of fusion? Mamiya.
It is the amount of heat energy that must be absorbed by 1 kilogram of a substance
Exactly.
at its melting point in order to change its state from solid to liquid at a constant temperature.
So it's just similar to specific heat capacity. Okay, heat capacity refers to the amount of heat energy that must be absorbed or liberated by a substance in order to raise its temperature by 1 degree Celsius or 1 Kelvin. Then specific heat capacity is the amount of heat energy that must be absorbed or liberated by 1 kilogram mass of a substance in order to raise its temperature by 1 degree Celsius or Kelvin. Specific latent heat of fusion of a substance is also the amount of heat energy that must be absorbed or liberated as well. Either you can absorb or liberate it. Absorb or liberated, okay, by a substance at its melting point. Okay, by 1 kilogram mass of a substance at its melting point in order to change state from solid to liquid, okay, at a constant temperature. That is all. So here it is like, because different substances, different solids would absorb heat energy differently in order to change state from solid to liquid. We are interested in the amount of heat energy that must be absorbed by 1 kilogram mass of different materials at their melting point in order to change states. So this is to a specific unit mass, which is 1 kilogram. Okay, and this is a general mass. So the amount of heat energy that must be absorbed or liberated by a unit mass. The unit mass can be 1 kilogram or 1 gram. A unit mass of a substance at its melting point in order to change states. In order to change state from solid to liquid at a constant temperature. Meaning, when it is changing states, its temperature must be constant. Now, if I'm giving m mass of a substance, m kilogram of a substance, to calculate for the amount of heat energy that must be absorbed by the substance in order to change from solid to liquid, how do I calculate it? You see, knowing what 1 kilogram can do, okay, knowing the amount of heat energy that must be absorbed by 1 kilogram, I can use that to calculate for any given mass. So for m kilogram mass, the quantity of heat energy that must be absorbed in order to melt, fusion, is equal to the given mass times the specific heat, the specific latent heat of fusion of 1 kilogram mass, LF. So assuming 1 kilogram mass require maybe 20 joules of heat energy in order to melt. If you give me 5 kilogram, the quantity of heat energy that must be absorbed would be equal to the given mass 5 times what 1 kilogram mass would absorb, 20. And that would be 100 joules. Okay, so if you want to calculate the quantity of heat energy that must be absorbed by any given mass of a substance, it must be the given mass times the latent heat of fusion, okay, of the substance, the specific latent heat of fusion of the substance. So this is how to calculate the quantity of heat energy required by a substance in order to change from solid to liquid. I want a volunteer to help me determine the SI unit of specific latent heat of fusion, LF. From the equation, help me derive the SI unit of specific latent heat of fusion. Priscilla, from this equation, help me obtain this. the SI unit of specific latent heat of fusion? Okay, Mamiya. Mamiya, I'm listening.
Sir,
Mm-hmm. Priscilla, go ahead.
so it's kilojoules per kilogram.
You are not wrong, but you are also not 100% correct, because SI unit of heat energy is not in kilojoules. Don't express it in prefixes. Just joule. Okay. So,
Joule per kilogram.
so joule per kilogram. This will be equal to joule per kilogram. Now, the specific latent heat of fusion of ice. The specific latent heat of fusion of ice is 335 kilojoules per kilogram. What does it mean? The specific latent heat of fusion of ice. Specific latent heat of fusion of ice is 335 kilojoules per kilogram. What does this statement mean? Yes, let me call somebody else to share. Frida, Frida, are you there? Oh, Frida Wada. Hello, Frida. Hey, people are not responding. The question is for you. And the statement is that the specific latent heat of fusion of ice is 335 kilojoules per kilogram. What does this statement mean? What does it mean? That ice has specific latent heat of fusion of that amount. Frida, can you tell us what it means? Oh, the gentleman who can help us. Okay. What do we mean by the statement that the specific latent heat of fusion of ice is 335 kilojoules per kilogram? Mamiya, what does it mean?
I think that it means that for every 1 kilogram of ice, we need 335 kilojoules of heat. For it has to absorb 335 kilojoules of heat to change into liquid.
Okay. So that's it. So, yes, what Mamiya said is correct. So it means that 1 kilogram mass of ice, 1 kilogram mass of ice must absorb 335 kilojoules of heat energy at its melting point in order to change state from solid to liquid at a constant temperature. So 1 kilogram mass of ice at its melting point melting point must absorb 335 kilojoules of heat energy in order to change state from solid to liquid at a constant temperature. That's basically what it means. That's basically what it means. And then the specific latent heat of aluminium is 396. The specific latent heat, the specific latent heat of fusion of aluminium is 396 kilojoules per kilogram. Eva, this one is for you. Eva, I beg you, tell me what this statement means. What does this statement actually mean? That the specific latent heat of fusion of aluminium is 396 kilojoules per kilogram. Eva, let's hear from you. Hey, you people don't want to talk. Wow. Even the gentlemen, the guys don't want to contribute. Oh, it's not healthy at all. Isaac Atta, I call you and you wouldn't speak. Isaac Atta. Prince. Only Mamia, sometimes Michelle, Eurefwa do contribute in class. And it's worrying. Okay, as usual. Okay, Priscilla. Frida, go ahead.
For every 1 kilogram mass of aluminium, the specific latent heat of fusion is 396 kilojoule to change the state from solid to liquid. The constant temperature.
Frida, you've done well, but it's not well so much polished. Let's polish it. Somebody else to help. What is the meaning of the statement that the specific latent heat of fusion of aluminium is 396 kilojoules per kilogram? Priscilla, can you come in? All right, so 1 kilogram mass of aluminium must absorb 396 kilojoules of heat energy at its melting point in order to change state from solid to liquid at a constant temperature. So 1 kilogram mass of aluminium at its melting point must absorb 396 kilojoules of heat energy in order to change state from solid aluminium to liquid aluminium at a constant temperature. Now for pure crystalline substances. For pure crystalline substances or materials, the quantity of heat energy that must be absorbed in order to change from solid to liquid, the same amount of heat energy must be liberated or evolved, given out, in order to change from liquid back to solid. For pure crystalline substances, if it is not alloyed, or if the substance is not mixed with any atom, the amount of heat energy that must be absorbed by 1 kilogram mass in order to change from solid to liquid, the same amount of heat energy must be liberated, given out to change from liquid back to solid. So, for instance, if you put water in a freezer, when the temperature drops to 0 degrees Celsius, okay, water begins to freeze. If every liquid water gets frozen and then you take it out of the freezer on a and then put it on a chair or a table, it would absorb heat energy. Don't forget, putting it in a freezer, you are taking the heat energy out of it. Okay, when everything gets frozen and you put it on a table, it would absorb heat energy. So whilst it is absorbing heat energy, when the temperature increases to 0, at 0, then it will begin to melt. So for pure substance, the amount of heat energy that must change state from solid to liquid, the same heat energy must be given out at the same temperature in order to change from liquid back to solid. Are we okay? Are we okay? Let's then look at latent heat of vaporization. We've done fusion. Let's also look at latent heat of vaporization. Vapor. Latent heat of vaporization also refers to the amount of heat energy that must be absorbed at the boiling point. So the amount of heat energy that must be absorbed at the boiling point of the material, of the substance, or at its boiling point, in order to change state from liquid to vapor at a constant temperature. And this is given by Q subscript V. This is given by Q subscript V. Some books also uses H for heat. Okay, so the amount of heat energy that must be absorbed at its boiling point in order to change state from liquid to vapor at a constant temperature is what is referred to as the latent heat of vaporization. Then here comes specific latent heat of vaporization. Kezia, are you there? Kezia. Oh, Kezia is gone. Kezia, you are here. Kezia, can you help me? What do we mean by specific latent heat of vaporization? Shortened as L to the subscript V. Kezia, Chairman. Kezia will not talk. Okay, Frida. Frida, over to you.
The amount of heat energy that must be absorbed by a unit mass of a substance at its boiling point in order to change its state from liquid to vapor at a constant temperature.
Simple. Okay. Simple. So please write it. Write it for me. Write it for me. Now the specific latent heat of vaporization of water is 2,311 kilojoules LV of water is 2,311 kilojoules per kilogram. And you see, for any given mass, the quantity of heat energy that must be absorbed in order to change from liquid to vapor at its boiling point must be equal to the mass times the value of a unit mass. So QV is given by this. Okay. Now, you see, because change of state occurs at a constant temperature, the reason for which you are not seeing delta T change in temperature in this one. Okay, so we are not seeing any change in temperature here because change of state occurs at a constant temperature. So the temperature from beginning will not change, okay, will be the same. So everything is done. So when you put water in a freezer at 0 degrees Celsius, water begins to change state. Please, it does not mean that at 0, every water has changed to ice. The change of state starts at 0. Then it will take some time. It will take some time for every liquid water to turn to ice. Okay, so the change of state occurs at freezing point of water, which is 0. But when it starts, the temperature does not change. So every liquid water turns to ice. That is why we are saying that change of state occurs at a constant temperature. So if the specific latent heat of vaporization of water is this, 2,311 kilojoules per kilogram, what does the statement mean? What does this actually mean? a volunteer to tell me. I'm not calling anyone. Feel free and then share what you think with us. A volunteer to volunteer. Let's not waste time. Hey. Oh, but I'm highly disappointed in the way some of you, respond to question answering. Please, you cannot, you see, we are learning. Just try. Frida, the rest of you, please, we are learning. Make all the mistakes and learn from it. Frida, go ahead.
I think for every 1 kilogram mass of water at its boiling point must absorb 2,311 kilojoules of heat in order to change its state from liquid to gas at its constant temperature.
Please. Okay, so basically what it means is that, just as Frida said, 1 kilogram mass of water must absorb 2,000. Okay, so Frida, usually start from 1 kilogram mass of water must absorb 2,311 kilojoules of heat energy in order to, at its boiling point, in order to change state from liquid, okay, to vapor at a constant temperature. That is all. That is all. Please, any question? Any question? No question. Okay, if no question, let's solve a problem. Let's solve a problem. So please, if water must change state from vapor back to liquid, then for pure water, undiluted water, this amount of heat energy must also be evolved or emitted, liberated to the environment at its boiling point. Okay, the boiling point of water is 100 degrees Celsius, meaning that when water is heated and absorbs heat energy, when it gets to this temperature, that is when water would change state from liquid to vapor. If you must cool condensation, cool water vapor, okay, when it gets to 100, you see, when heated, its temperature, when it turns to vapor, when water turns to vapor, its temperature after everything has change states can increase. Don't forget I said change of state occurs at a constant temperature. So when water is heated, it gets to 100, water starts to turn to vapor. After every liquid water has turned to vapor, the vapor can be heated and then go beyond 100. If you must cool it, condense it, when the temperature gets to 100 degrees Celsius, that is the point where vapor begins to turn to water, liquid water. Is that okay? At a constant temperature. Now, if it is pure water that is heated to turn to vapor, it must also give out this same amount of heat energy for 1 kilogram mass of that to change to water. So it's a vice versa situation. Please, any question? Any question? All right. Assignment to the house. assignment. And listen to the question so attentively. How much heat energy? How much heat energy is required to convert 5 kilograms of ice at 0 degrees Celsius? How much heat energy is required to convert 5 kilograms of ice at 0 degrees Celsius into 5 kilograms of steam at 100 degrees Celsius? How much heat energy is required to convert 5 kilograms of ice at 0 degrees Celsius into 5 kilograms of steam vapor at 100 degrees Celsius? Take the latent heat of fusion of ice to be 335 kilojoules per kilogram. The specific latent heat of fusion of ice, you need this constant, so I'm giving them to you. The specific latent heat of fusion of ice is 335 kilojoules per kilogram. The specific heat capacity of water is 4.2 kilojoule per kilogram per Kelvin. The specific heat capacity of water is 4.2 kilojoules per kilogram per Kelvin. And the specific latent heat of vaporization of water is given by this amount. Okay, I'm going over the question. How much heat energy is required to convert 5 kilograms of ice at 0 degrees Celsius into 5 kilograms of steam at 100 degrees Celsius? Take the specific latent heat of fusion of ice to be 335 kilojoules per kilogram. The specific heat capacity of water, 4.2 kilojoules per kilogram per Kelvin. And the specific latent heat of vaporization of water is 2,311 kilojoules per kilogram. That is your assignment. Okay. All right. So I think we'll end here. We'll end here and then continue next week. But to be very frank with you, today, your reluctance in answering questions has actually demoralized me. I'm completely demoralized. You know, share your view and it's a trouble. In fact, it doesn't help teaching and learning at all. So you better, the gentleman, I beg you, you better come again. And some of you girls must also, after all, we are learning. Getting something wrong is part of learning. So do not hesitate to express what you think you have. Even to the extent that some of you are pretending not to be there. It doesn't augur well at all. Learn and try and turn over a new leaf in our next meeting. We'll continue with the optical instruments on Friday. So expect my call. So we go through the optical instrument. So this is where I end today's show. Please take care of yourselves and then may the good Lord be with you. Bye-bye.
Bye.
Mhm.
Bye.